So this week we're doing renal. Congrats, you made it to the last anatomy exam. That's so exciting. So 3 more units. Reminder, my office hours are tomorrow. Come ask me questions, anything. Also a reminder that you can ask me about like research or other things too. You don't have to just ask me about anatomy if you want to come to my office hours or email me. There's my email. I couldn't find a typed study guide again for these last few units. I guess I didn't type the last 2 exams. But I did make like a summary terms list. So basically that's me just going through my notes and writing down terms that I'm like, oh, that, like just organizing kind of all the information. So it's kind of helpful when you're studying to use that. Maybe you can look at it, it's up. And then there's also a practical study guide up. I know that's coming up for 2 weeks, I think, for you guys. So feel free to use that. Bless you. Okay, so the first few slides, I just kind of am going over general anatomy just to kind of set the stage for what we're talking about. So renal system overview, main function is to filter the blood, to get anything out of the blood that you don't want circulating in your body, to then get into waste, which you excrete out. And that's done in the kidneys. And the functional unit that's doing this, like the smallest kind of unit that does it all by itself, is called the nephron. So zooming out on this whole system, you have the kidneys that then run the filtrate through ureters to the urinary bladder where the urine is stored. And then you have the urethra, which then takes the urine out of the body. Then zooming in on the kidney, there's the cortex, which is the outer layer, then the medulla, which is the inner area, and this contains the renal pyramids. And then you got those calyces with the minor and major regions. And then there's the nephron, which is kind of within those regions. And there are 2 types of nephrons, the juxtamedullary and the cortical nephrons. And then parts of the nephron. I kind of just put these first few slides just to kind of like get us thinking about what we're going to talk about. So then here's the functional unit. You have the Bowman's capsule where the blood kind of comes in, and then parts of the blood that want to leave the blood and get excreted go into the tube. So then it runs through the proximal tubule, down into the loop of Henle, and then the distal convoluted tubule into the collecting duct. Something else I wanted to mention with this picture is you can see how the blood is coming from that main artery and running right into the kidneys, which is cool because the blood circulating from your body goes into your kidneys, is kind of like cleaned up, and then enters back into circulation. This is a really blurry picture, but now we're zooming in on the juxtaglomerular apparatus. So you have an arteriole entering, which is the afferent arteriole. Due to pressure, blood is filtered and some stuff enters the tubule, and the stuff that enters is known as filtrate, and then the blood that's cleaned leaves out of the efferent arteriole. Okay, so now 2 major terms to keep straight while we're talking about this stuff is the difference between filtration and reabsorption. So filtration refers to stuff leaving the blood and entering the tubule in the nephron. So filtration, leaving the blood, entering the urine. This is non-selective, and it mainly happens in Bowman's capsule due to hydrostatic pressure. So when blood is entering from a bigger volume into a small space, the blood's kind of pushing against the wall, and that just kind of like pushes some stuff out into the tubule. That's then known as filtrate because it's in the nephron. Reabsorption, on the other hand, refers to taking the stuff back from the filtrate in the nephron back into the blood. So you're not going to lose it. It's being reabsorbed almost back into the body by re-entering the blood. This can either be semi-selective through transporters or selective and happen through active transport using energy. And reabsorption occurs through the rest of the nephron. So it's in the proximal tubule, the loop of Henle, the distal, and collecting duct. This slide outlines what is happening in each part of the nephron. So like we talked about, blood entering Bowman's capsule or the renal corpuscle is filtered. So materials come out of the blood and enter the nephron. And then throughout the rest of the nephron is reabsorption. So stuff is coming out of the nephron and re-entering the blood. And in specific regions of the tube, specific things are reabsorbed. So if I'm correct, or at least when I took this class, did you guys do the drawing with like at different parts of the tubule with the different transporters in class? No, you did not do that. You probably do it tomorrow. Okay, I bet you'll do it tomorrow. I'm gonna skip this for now just because I have another drawing I want to do, and I think you do this in class. But I have my drawing I think you do tomorrow here. So what this is going through, if we have time, we'll come back to it. But the orange box, for example, it's kind of hard to see if you don't have it on your computer, is the proximal convoluted tubule. And that is a cell on the side of the tubule. So if you have the tubule, like, just to give you like context, that square is just like, this is like the blood. This is like inside the nephron, so you could also say filtrate. Each of the boxes kind of refers to what the materials have to go through to either enter or exit the filtrate. So I have all of the transporters on there for you to reference while you're studying. Today I more wanted to focus on regulation. So there are 3 forms of intrinsic regulation in the nephron. So first you have the juxtaglomerular apparatus, and I'm going to draw this out, but there's nitric oxide and adenosine that can be released due to different conditions in the JGA. And there's also the myogenic response, which kind of refers to like a muscle response, almost you can think of it as. So if the blood vessel is stretched, then there's some sort of like indication, and then the myogenic response refers to then it constricting, just to kind of keep it regulated. So if there's a lack of stretch, then the myogenic response would vasodilate the arteriole to try to like help more blood be pushed through. to increase the glomerular filtration rate. And then there are a bunch of hormones that we're going to go over that help regulate the GFR. So it's important to understand kind of the effects that the hormone is going to have in relation to the glomerular filtration rate. So the hormones are secreted specifically to either increase or decrease the glomerular filtration rate, which then has an impact on blood pressure. So if you ultimately decrease the glomerular filtration rate with a hormone, then you're increasing blood pressure. Decreasing the glomerular filtration rate allows more sodium to be reabsorbed, which water follows, which increases blood pressure. Does that make sense? Okay. Increasing the glomerular filtration rate, on the other hand, will decrease blood pressure because less sodium is going to be reabsorbed because we're going through the nephron really fast. It can't get all of the sodium out. So then less water is reabsorbed into the blood and your blood pressure goes down. So here's a summary of the hormones and their effect on blood pressure. So aldosterone, ADH, and the RAS system, or the renin-angiotensin, I forget the second A system, aldosterone system. Those all increase blood pressure by decreasing the glomerular filtration rate. So they all help more sodium and therefore water be reabsorbed into the blood to increase blood pressure. To decrease blood pressure, ANP is the hormone that's released. To increase glomerular filtration rate, so less sodium and therefore water is reabsorbed. So just to see if you guys understand this, if I asked what hormone would be released if there's high blood pressure, which one would you say? Yeah. Because the wording can get a little, because the goal of ANP is to decrease blood pressure, so it would be released when there's high blood pressure. Okay, so this is where we're gonna draw. I think let's have a light on. Okay. So this is going to be of autoregulation in the kidney. Autoregulation in kidney. Okay. So I'll go back to this slide while I talk about this. So the first way that you can kind of like regulate what's happening in the kidney or filtration is in the juxtaglomerular apparatus. So in the JGA if there's a low GFR, which means that the glomerular filtration rate is low. It's not a lot of blood is coming through. Low glomerular filtration rate. Then nitric oxide is released. And what nitric oxide does is it vasodilates that afferent arteriole to try to increase the glomerular filtration rate. So vasodilation Okay, so I'm also going to bring us back to here. So glomerular filtration rate kind of just refers to how fast we're bringing blood in from the body and filtering it through Bowman's capsule. So if it's low, then it's going slow, and if it's high, then it's going faster. So if we have a low glomerular filtration rate, releasing nitric oxide dilates the afferent arteriole. So this arteriole right here, it's going to get wider, which allows more blood in and then increases the rate of filtration. Does that make sense? Does anyone have any questions? I feel like people are confused. Do you guys want me to say that again, or you got it? Yeah. So basically, if filtration is really slow, we're not getting a lot of stuff coming out of the blood into the Bowman's capsule. By dilating this afferent arteriole that's bringing the blood in, we can allow a greater volume of blood in and then increase the filtration rate because more blood is coming in faster, so filtration is going to increase. So dilation means to make the radius bigger, allows more blood in, increasing filtration. Does that make more sense? We'll move, maybe it'll make more sense as we go on. So the next thing that the JGA can do is the opposite. If there's a high filtration rate, then adenosine is released. And what adenosine does is it constricts the afferent arteriole. So maybe this one will make more sense. The filtration rate in Bowman's capsule is too fast. There's too much blood running through and the body cannot keep up. So adenosine is released. The afferent arteriole bringing blood into the Bowman's capsule constricts, it gets smaller, allowing less blood in, slowing down filtration. Does that make sense? Okay. So they're opposite responses. And then the second type of of regulation is the myogenic response. Which is the kind of direct response of the smooth muscle. So if the afferent arteriole is stretched, that means that there's a lot of blood in there and the filtration rate is really fast. So the myogenic response just constricts the blood vessel to try to like regulate the filtration rate. So it kind of leads to, it constricts. And then the opposite is also true. So if it's not stretched, then it will dilate. Which I have on here. Lack of stretch leads to vasodilation. Now, getting into the hormones. So there are 3 that work to increase blood pressure. So these ones are released to increase blood pressure, which also means that they're decreasing the glomerular filtration rate to then help aid in the reabsorption of sodium and the reabsorption of water. So here, there's aldosterone. And it's stimulated by 2 different factors. So it's stimulated by Does anyone have a guess as to what one of the reasons or one of the things that helps aldosterone get released is? Any guesses? So it's released to increase blood pressure. So something that stimulates its release is low blood pressure, as we'll see in a lot of the hormones on this side. Stimulated by low blood pressure, I don't like the, to help increase blood pressure. And then it's also stimulated by potassium in the plasma. And then it works to help increase sodium absorption and increase blood pressure. increase NA reabsorption, which increases blood pressure. Second one is ADH, or vasopressin. ADH again is stimulated by low blood pressure. Another indicator of low blood pressure that also stimulates the release of ADH is less stretch in the aorta. So if I told you there's decreased stretch in the aorta, you can assume that blood pressure is low, because you have like a smaller, almost like volume of blood. And then also a high plasma osmolarity. And the ultimate outcome of ADH is to insert more UTA into the collecting duct to help reabsorb more water. So you insert, which is one of those transporters in the picture, in the slides that I think you'll go over tomorrow in class. More reabsorption. And then you're going to increase blood pressure. And then there's one more hormone that helps increase blood pressure, or it's multiple hormones. It's the renin angiotensin aldosterone system, or RAS. So first, renin is released. When there's low sodium. So it's stimulated by low sodium. If you think about that, low sodium in the blood would correlate to low blood pressure. So it's stimulated by low sodium, so we want to increase blood pressure. Renin, when in circulation, encounters angiotensin, which is a protein, and then it converts angiotensin, I'm gonna write protein, it kind of just finds that in circulation and converts it to angiotensin 1. And then at the lungs, some sort of enzyme that converts it to angiotensin 2. which then increases blood pressure by acting in a bunch of different ways. So, to review, renin is initially released, hormone that circulates in the blood and encounters angiotensin. Angiotensin converts renin into angiotensin 1, encounters this enzyme in the lungs, which converts to angiotensin 2. Angiotensin 2 increases blood pressure by releasing ADH, which is this hormone over here. And also aldosterone, so it releases both of those hormones. Increasing thirst, which is cool because then you're increasing your water intake, so that will help increase your blood pressure. And vasoconstriction. Systemic vasoconstriction helps increase blood pressure. Okay, and then we have one more hormone to go over that helps decrease blood pressure. So this one's released to decrease blood pressure. And this is ANP. It's released when stretch receptors in the heart sense a high blood volume. So that would indicate high blood pressure. So we're trying to decrease blood pressure. So it's stimulated by stretch receptors in the aorta. So that's indicating high, I won't write that, but it's indicating high blood pressure. And then it acts by decreasing the secretion of both of these hormones that increase blood pressure. So then you decrease ADH release and decrease aldosterone release. Which decreases blood pressure. And increases the glomerular filtration rate. So hormone 1, 2, this is like a system, this is the hormone, and 4. And I have that here too, so you can reference that. I know these are kind of confusing. That's why I wanted to go over them because it's hard to keep straight the glomerular filtration rate and blood pressure. But if you think through kind of what's happening, it helps you understand better what's going on. Does anyone have any questions about anything that we went over here right now? Okay, I'll keep going. So everything we talked about here is autoregulation in the kidney, so it's kind of local regulation by like the nephron. There's also systemic arterial regulation to regulate blood pressure also, so I wanted to mention that here. So if you want to increase your blood pressure, you would vasoconstrict systemically. If you just think about having low pressure in all of the vessels in your body, constricting them would increase the pressure. So low systemic blood pressure, the body would then constrict to try to increase blood pressure. And to decrease blood pressure, the body vasodilates systemically. Okay, so I have some top hat questions. Okay, first one. Which of the following hormones or systems would not work to increase blood pressure? Okay, so most of you have answered. This right here is just referring to what we just talked about. These three hormones are released to increase blood pressure: aldosterone, ADH, and then the RAS system. ANP is released to decrease blood pressure. There you go. All got it. Nitric oxide, what does it do? Okay, so the first one, A, is constricts the afferent arteriole, decreasing GFR. So the answer, if I asked about adenosine, that would be the correct answer. Systemic vasodilator. Nitric oxide does vasodilate, but it only works on the afferent arteriole. Systemic would mean it affects all of the arteries in the body. So it can't be that one. And then dilates the efferent arteriole should be the correct answer. Increasing the glomerular filtration rate. Local vasoconstrictor would also apply to adenosine. Systemic vasoconstriction increases or decreases blood pressure. So this one is increases blood pressure. What I kind of think of in my head is all of the arteries kind of like this. If we have low blood pressure, this isn't like correct, but say the blood was just kind of like filling up that much of the artery, then the artery is like, there's really low pressure in the body. Like, it can't even stay open. It's probably gonna look like something like this. And that's really low pressure. So what the body does is it constricts, makes it smaller. So then the blood could kind of fill up the whole entire space, and the pressure is now regulated. That's how I think about it. If that helps. What two forces, I didn't go over this, but it is in the videos. What two forces oppose filtration by drawing material back into the blood in Bowman's capsule? And there are two correct answers. So quickly to go over this, you have Bowman's capsule, kind of looks like that, and then you have the afferent arteriole bringing blood in, efferent bringing blood out. There's one force that kind of helps materials enter the filtrate, and that's the glomerular blood hydrostatic pressure. So it's kind of just pressure due to decreasing volume and entering the small space, pushes stuff into the filtrate. CHP and BCOP are two different forces that help push materials back into the blood. That's CHP and BC. True or false? The urethra carries filtrate from kidneys to the bladder. We're pretty split on this one. So this one's actually false. Kind of just reminding you to be careful, even though with the macroanatomy, because you can get really caught up in the small things. It goes kidneys, ureter, bladder, urethra. Because ureter and urethra sound really similar. Increasing sodium absorption, and there are two correct answers. What effect does sodium have? So, increasing sodium, then sodium retention or reabsorption increases water retention, which increases blood pressure. Water follows sodium. So when sodium is reabsorbed, water is reabsorbed, and blood pressure increases. I didn't go over this again. This has to do more with these transporters, this slide. So we'll see how you guys do on this. Urea is secreted where? So urea is secreted in the descending loop of Henle. You can notice here that there are 3 different regions of the loop of Henle to be aware of. You have the descending loop, and then the thin ascending loop, and the thick ascending limb. And there are different things being reabsorbed or secreted in each region. But urea is secreted in the descending loop. And then I have one more thing I wanted to show you. This is the term summary I have. So just looking at it, you can see I kind of just like wrote down words. So when you're studying, you can kind of be like, I feel like it just helps you like group terms together and relate things. So yeah, I just wanted to put that up, show you that it's there when you're reviewing. But that's all I have. Feel free to stay and ask questions or come to office hours. But thanks for coming.